We move over to another example on formation of ordinary differential equation. So this example says y squared is equals to 4a bracket x plus a. We are meant to find the ordinary differential equation that is corresponding to this equation. In this equation, how many constants do we have? We actually have only one constant, although they appeared in two places, but it is still one constant. So therefore, we need to differentiate once. For solution, y squared is equals to 4a x plus a. Call this equation 1. To differentiate these, I love writing this separately so that I won't be confused and it will make it easier for me to differentiate. Therefore, differential of y will give us dy over dx multiply with y, dy over dx multiplied with y, plus the differential of this y, the y over dx multiplied with y, which is equals to, if you differentiate this, if you differentiate 4a, 4a is a constant. If you differentiate a constant, it's going to give you 0. Multiply with this, it's going to give you 0. Plus, if you differentiate x plus a, it's going to give you, if you differentiate x plus a, it's going to give you 1. Then that one multiply with this constant, which is 4a, is going to give you 4a. So if you differentiate this, it's going to have 4a. Putting this together, we're going to have y dy over dx plus y multiply dy over dx, y dy over dx, which is equals to 4a. Y dy over dx plus y dy over dx, we have 2y dy over dx, which is equals to 4a. Now, since y dy over dx is now equal to 4a, since 2y dy over dx is equals to 4a, and if you look at equation 1, they show no resemblance. We cannot factor anything out. We cannot make anything the subject of the formula to make it look like equation 1. So from here, we have to disobey how many times we have to differentiate, but to differentiate again, because here, in this type of situation, we are helpless, and the only way is to differentiate again. So differentiating this again, this 2 is a constant, bringing out 2. Y dy over dx is equals to 4a. Differentiating this, going to have differential of y is dy over dx multiply with this dy over dx, plus differential of this dy over dx is the squared y over dx squared multiply with this y, which is equals to, if you differentiate 4a, is going to give you 0. 4 is a constant. Therefore, 2 bracket dy over dx multiplying each other, we have dy over dx all squared plus y the squared y over dx squared is equals to 0. 2 multiplying, opening bracket, 2 multiplying the 2, you have 2 dy over dx all squared plus 2y the squared y over dx squared is equals to 0. Therefore, rearranging in order of the equation, second order first because it's the highest, we have 2y the squared y over dx squared plus 2 dy over dx all squared, which is equals to 0. Therefore, we say this is the ordinary differential equation that is corresponding to this equation. Now, we move over to another example, which is y is equals to a e raised to power x plus b cos x. In this, we have two constants. Therefore, we need to differentiate two times. Therefore, solution, differentiating let's write the equation. Y is equals to a e raised to power x plus b cos x, equation 1. Differentiating once, going to have dy over dx, which is equals to, if you differentiate this, it's still going to give you a e raised to power x, plus if you differentiate b cos x. First of all, what I told you is differential of b, which is a constant, multiplying cos x is going to give you 0, because the differential of b is a constant. Differential of b, a constant, is going to give you 0. Multiply with cos x is going to give you 0. Plus differential of cos x is minus sine x. Multiply with b, you're going to have minus b sine x. Opening bracket, dy over dx is equals to a e raised to power x minus b sine x. Call this equation 2. Now we need to differentiate again. The squared y over dx squared is equals to, if you differentiate this, you're still going to have a e raised to power x minus, if you differentiate b, which is a constant, multiplying with sine x, is going to have 0, because differentiating b is a constant and is 0. 0 multiplied sine x is going to give you 0. Plus, if you differentiate sine x, is going to have cos x. Multiply with b, going to have b cos x. Call this equation 4. We have differentiated 2 times, and if you look at these equations, there is no way we can make equation 4 to look like equation 1. There's no way we can make equation 3. This is equation 3, sorry. There's no way we can make this equation 3 to look like equation 1. It's not possible to even make it to look like equation 2, because this, we have minus b sine x here, but here we have minus b cos x. We can only make it look like equation 1, but it's not possible, because even if I go to factor out minus, even if I say minus a e raised to power x plus b cos x, so that it will look like this equation. But these two things are not the same thing, because when minus multiplies, it will be minus a e raised to power x minus this times plus, this minus times plus give us minus b cos x. You know, these two equations, these two things are not the same. Here is positive, here is negative, so we can't do this. So whenever you arrive at this situation, the only way for you to go is to differentiate again. And differentiating again, what are you going to have? The cube y over ds cube is equals to, differentiating this, is going to have a e raised to power x. If you differentiate, keeping this minus, if you differentiate this, differential of b, which is a constant, is 0, multiplying with cos x 0 is going to give you 0. Differential of cos x is going to give you minus sine x, minus sine x times b is going to give you minus b sine x. So minus b sine x. Opening bracket, going to have a e raised to power x minus times minus is going to give you plus b sine x. Call this equation 4. Now, what we are going to do now is this. We are going to try to equate the equations with the ones that are likely close to each other. What do I mean? From equation 1, this is equation 1, this is equation 2, this is equation 3, and this is equation 4. So, if you look closely, in equation 1 we have cos x, and equation 3 we have cos x. In equation 2 we have sine x, in equation 4 we have sine x. So what we do is add equation 1 and equation 2. If you add these two equations, y is equals to ae, this is equation 1, y equals to ae raised to power x plus b cos x. This is equation 1. If you add it with equation 2, dy over dx is equals to ae raised to power x minus b. If you add this equation 1 with equation 3, minus cos x, we add equation 1 and equation 3 together, and also add equation 2 and equation 4 together. Adding equation 1 and equation 3, if you add these two equations, you're going to have dy over dx plus y, this plus this, is equal to, if you a e raised to power x plus a e raised to power s is going to give you 2a e raised to power x. B plus b cos x plus minus b cos x is equals to b cos x minus b cos x, and b cos x minus b cos x is equals to 0. Therefore, no need to add plus 0 here. Therefore, adding these two equations, this is what we get. And also, we need to add equation 2 and equation 4, which is equation 2 is dy over dx. Sorry, this equation 3 is the squared y over ds squared. Yes, this equation 3 is the squared y over ds squared. Adding equation 2 with equation 4, equation 2 is dy over dx, which is equals to a e raised to power x minus b sine x. This is equation 2. Adding it with equation 4, which is the cube y over dx cube, which is equals to a e raised to power x plus b sine x. Adding these two equations, we have the cube y over dx cube plus dy over dx is equals to a e raised to power x plus a e raised to power x is going to give us 2a e raised to power x minus b sine x plus b sine x is going to give us 0, because minus b sine x plus b sine x is going to give us 0. Therefore, we look that this dy over dx plus y is equals to 2a e raised to power x. The cube y over dx cube plus dy over dx is equals to 2a e raised to power x. Since this is equation 5 and this is equation 6, since equation 5 and 6 are equal to the same thing, are equal to the same result, what we can do here is simply compare the both equations. So, comparing the two equations, which is equation 6 and equation 5, comparing these two equations, since this is equal to this and this is equal to this, and two of them are equal to the same common equation, therefore we say that the cube y over dx cube plus dy over dx is equal to this. Substituting this for this is equals to dy over dx is equals to the squared y over dx squared plus y. This is the squared y over dx squared. The cube y over dx cube plus dy over dx is equals to the squared y over dx squared plus y. Now, equating everything to 0, the cube y over dx cube, the squared y over dx squared is positive. Moving over to the other side is going to be negative, minus the squared y over dx square plus dy over dx. This y is positive, moving over to be negative, minus y is equals to 0. Therefore, we say that this is the ordinary differential equation that is corresponding to this differential equation.